An electric field is defined as a field of force surrounding a charged particle. It can also be defined as electric force per unit charge, or E equals F over Q. Electric fields can occur in a point charge, between multiple point charges, in a charged cylinder, or parallel plates. In this video, we will discuss mapping electric fields for point charges and parallel plates, calculations, and applications. The electric field of a point charge can be mapped using lines that emanate towards or away from a charged particle in all directions. The field is mapped as vectors which indicate the magnitude and direction of the electric force that would be experienced by a charged particle of +1 coulomb. Electric field of a positive point charge. Here we have a positively charged particle and a test charge near it. Due to repulsion between likely charged particles, a test charge of +1 coulomb would accelerate away from the positive charge. Therefore, the field vectors on a positively charged particle all point outwards like so. To draw an electric field on a negative point charge with a positive test charge must be considered. Due to their attractive properties, the positive test charge will accelerate towards the negative particle. Therefore, the electric field vectors point towards a negatively charged particle. In addition to point charges, an electric field can occur between two parallel plates like these. The one on the top is positively charged and the one beneath it will be negatively charged. Similar to the point charges, we can draw an electric field between the two plates based on their charges. The field created by the positive plate will emanate away from the positive charge, and the fields created by the negative plate will emanate towards the negative charge. We can label the force between the plates as E1 for positive and E2 for negative, and Q1 for the positive plate and Q2 for the negative plate. In addition, these vectors can be added, and the electric field can be drawn as simply traveling from the positive end to the negative end. Additionally, the electric field above and below the plates can be analyzed. Below the plate, E1, the field created by the positive plate, is directed away from the positive plate, and E2, the field created by the negative plate, is directed towards the negative plate. These are equal and opposite forces, resulting in a net force of approximately 0. The same concept occurs above the plates. In parallel plates of infinite length, the net force is equal to exactly 0. Using the same principles regarding vector addition, we can draw the net electric field between these two point charges that are of opposite charges of equal magnitude. In order to construct the net electric field, we must consider the net electric field between these 2 points. At point A, we have Q2 emanating a field away from it. This will be labeled as E2. And we also have a field directed towards the negative charge Q1, and we will label this as E1. Because point A is much closer to Q2 than Q1, E2 would have a higher magnitude than E1, meaning that the net electric field is directed towards the right. Similarly, at point B, we have E1 being directed towards the negative charge, and we also have E2 being emanated away from Q2, but due to the larger distance between Q1 and Q2, E1 will have a greater magnitude than E2, meaning that the electric field is also directed towards the right at this point. So putting together what was stated before, the electric field on the middle line of these 2 points is straight, pointing towards the negative charge. However, as you deviate away from the center line, the electric field begins to be slanted, such as this point or this point. The electric field would slant in this direction and this direction. Therefore, by taking into consideration the net electric field at all of the surrounding points, As the point deviates further from the center, the net electric field becomes more curved. So the overall net electric field between these 2 points would be drawn like this. This interaction between the 2 fields is what we call an electric dipole.
There are 2 main types of calculations that one can do using electric fields. The first involves point charges, and the second involves parallel plates. So let's first start with point charges. Suppose we're given a system with just one point charge, and the charge is Q. Then at a distance of r away from that point charge, the electric field strength can be given by the equation E equals K times Q over r squared. And in this case, K is the Coulomb's constant, which is 8.99 times 10 to the 9th power. And just by looking at this equation, you may notice a similarity with the Coulomb's law because it's actually derived from it. And from this equation, we can tell that the electric field strength is directly proportional to the point charge Q, and it has an inverse square relationship with the distance r away from the particle. This equation may be used to do dynamics calculations. So if we set up an equation using the standard definition of electric fields, as well as our given equation, then we can solve for the force, which allows us to answer dynamics questions that may be required. Now let's move on to calculations with parallel plates. So when working with parallel plates, we must first make the assumption that we are somewhere near the center of the plates, so that the electric field lines are actually straight, as shown in this picture. So if we have a system of parallel plates with opposite charges of Q and areas of A, then the electric field created between the plates is given by the equation Q over epsilon times A, where epsilon is the electric constant, and that is equal to 8.85 times 10 to the negative 12th power. The electric field is actually constant throughout the region between the plates, and this means there's also a constant single direction force between them going from the positive charged plate to the negatively charged plate. And this has the interesting effect of allowing us to do kinematics calculations. So if we set up the equation using the standard definition of electric field as well as our given equation, then once again we can solve for force, which is the force going from the positively charged plate to the negatively charged plate. And we can think of this force just like gravity in a projectile motion problem. So if we have a particle in between these plates, then this charge will cause it to be affected by this electric force, and we can find this trajectory using kinematics calculations.
The first and most well-known application of electric fields of point charges and plates can be seen in the cathode ray tube. The plates labeled vertical and horizontal deflection plates are given a charge through external batteries. This allows for the beam of high-speed electrons coming from the gun to be manipulated as they move toward the cathode. Giving each plate a negative or positive charge causes the electrons to be repelled or attracted by the electric field, therefore allowing them to be bent or more inclined to be moved towards one portion of the cathode. All of this can be done in only fractions of seconds, as the charged particles move at extremely high speeds. Michael Faraday proposed these ideas that helped humans to understand manipulating electron beams, which have been especially important in television, so we can thank him and his work in electric fields for things like Netflix that we use so readily today. The second application that I'm going to describe today is gel electrophoresis. The endgame of this highly popular technique is to separate macromolecules and substances. Gel electrophoresis is most commonly used as a DNA analysis tool in biochemical laboratories, and is conducted by generating an electric field along a gel plate, then placing a DNA sample at the negative end of the plate. The negatively charged DNA molecules are compelled by the electric field to migrate across the plate. The movement of the molecules is resisted by the gel, so smaller molecules move much faster than the larger ones. As a result, over time, distinct linear clusters of molecules form, allowing for more clear analysis on the composition of the sample to be pursued by scientists. This setup is similar to that of parallel plates described by Daniel later in the PowerPoint.